piece of advice number one, make sure you do problems. That's what we're doing today. But there's lots of problems out there. Quiz problems, old exams, other review problems. Now, of course, there's so many problems you can't possibly do them all. But try to say, where do I need some work? And work on some of those problems. You should have a pretty good idea of what's coming. And of course, the second piece of advice, take care of your health. Eat some good food, like nuts. Go outside. The weather's nice right now. Enjoy it a little bit this week. Don't just sit inside the library. I mean, the library's nice, but get some fresh air. Get some sleep. And as I say, if you need to yell into your pillow, that's fine. Pillows are made to be yelled into. It's one of their designs. All right. Well, with that out of the way, 10 problems. My goal is to make it under 2 hours. That's always my goal, but I'm serious this time. I'm going to go for it. Number one. So find the following. The Laplace transform of some long expression. And, okay, part B says this integral. Okay, all right. So we'll do these in order. So part A. The Laplace transform of e to the 3t minus t plus 2 cosine t quantity squared. Okay, well, what do we do? And this comes back to how do we do problems? And the punchline is that most of the math that gets done is a matter of just rewriting things to the point where it's like, okay, I've rewritten it, I can apply my rule. And that's true for this part A. And you might say, well, okay, we understand how to do e to the 3t, we understand how to do t, we understand how to do 2 cosine t. What's so hard? What's tricky about this? Well, the problem is there's this square here. And how do you handle the square? Well, unfortunately, Laplace doesn't work great with squares. It works great with addition. It works great with constants. It does not work great with squares. So what do we need to do? Well, no big surprise. Let's rewrite the inside. And we'll make it so it's friendly. When I say friendly, something where we have rules. Rules are very helpful for solving things. All right, so we're not doing the Laplace yet. We're just working on the inside. So to square something, we're going to multiply this all out. E to the 3t minus t plus 2 cosine t times e to the 3t minus t plus 2 cosine t. Okay, well, what comes next? What do you do? What's the technique called? Foil. It's kind of, convolution also is somewhat related, but here it's just, another word is distribution. And you might say, are we really allowed if there's multiple terms? And the answer is, of course. The rule is, multiply every term from the first part with every term from the second part, and just be very patient and make sure you don't forget anything. All right, e to the 3t times e to the 3t will give us e to the 6t. You add the exponents. All right, e to the 3t times minus t, minus t, e to the 3t. And e to the 3t times 2 cosine t, 2 e to the 3t cosine t. No surprise there. Okay, now we'll go to the middle term. We have minus t times e to the 3t, which, that's another minus t e to the 3t. So there's actually a pair of them. That's all right. Minus t times minus t plus t squared minus t times 2 cosine t minus 2t cosine t. Okay, and one more layer. And okay, so the 2 cosine t term. So 2 cosine t times e to the 3t I did a bad job of lining things up. So 2 e to the 3t cosine t. 2 cosine t times minus t, that's minus 2t cosine t. And then 2 cosine t times 2 cosine t is 4 cosine squared t. All right. So you'll notice, if I had done a better job of lining things up, that there's 3 terms, the e to the 6t, the t squared, and the 4 cosine squared t. Those are all just being squared. And then the other terms will basically double up. Okay, so all told, put together, we can say the inside becomes e to the 6t plus t squared plus 4 cosine squared t minus 2t e to the 3t plus 4 e to the 3t cosine t minus 4t cosine t. Okay, so that's the square. All right, now remember we said that Laplace transforms are nice when it comes to addition. So if you have a bunch of stuff being added together, you say, look, I just treat them individually. So, are we happy with e to the 6t? Do we have a rule for that? Yes. T squared, do we have a rule? Yes. 4 cosine squared t? Let's come back to that one. 2t e to the 3t, well, 2 is a constant. Yeah, we just need, don't, put it aside. T e to the 3t, do we have a rule?
Yes.
Yeah.
I don't like it, but yes.
What do you mean you don't like it? It's a beautiful function. I mean, maybe you don't want to bring it home to your parents on the first date. Wait a few dates. But eventually, they'll warm up. All right, e to the 3t cosine t.
I'm just in a toxic relationship with convolutions.
We haven't even gotten there yet. But we will. Okay, that's good. T cosine t, is that good? Do we know that? Yes. Now, what do I mean by do we know that? It's on the formula sheet. And this one actually is on the formula sheet. I don't think it's on the handout I gave out, but it is on the formula sheet. Now, one piece of advice about this exam, don't try to be a hero. Use the formula sheet, because this, you will live or die based on whether or not you know the formulas. And so, don't try to force yourself to remember them. Double check. We gave it to you. We want you to pass. And we want you to do great. Okay, so everything's good except the 4 cosine squared t. So what can we do with 4 cosine squared t? Power reduction. And where might we find that? It's on the formula sheet. So really this is 4, and then cosine squared is a half, 1 plus cosine 2t. Okay, so rewriting this one more time, we have e to the 6t plus t squared. 4 times a half times 1 is 2. 4 times a half again, so that's 2 cosine 2t minus 2t e to the 3t plus 4 e to the 3t cosine t minus 4t cosine t. Now notice we haven't done any Laplace transforms yet. All of this is the rewriting so that the individual pieces are things that we can work with. And now they all are. So we're ready to answer the question. We say, okay, so we're going to take the Laplace transform of this. So we plug it in. And we don't have to worry which order it is. Our graders are smart enough to know. They'll figure it out. Well, that or they'll ask an easier question. One of those two. Okay. E to the 6t. Anyone have that off the top of their head? 1 over s minus 6. Good. T squared. How about that one? So the power is 2. So 2 factorial, which is 2. And then s cubed. How about 2? 2 over s. Very good. So the 2 is a constant. The Laplace transform of 1 is 1 over s, so you get 2 over s. Okay, then you have 2 times cosine of 2t. Well, we know the Laplace transform of cosine of bt, or constant times t. So for the cosine, it's s over s squared plus 2 squared, so s squared plus 4. Okay, how about t e to the 3t? What happens there? So for t e to the 3t, we're going to combine 2 things together. There's a rule that says the Laplace transform of t is 1 factorial over s to the 1 plus 1, which is 1 over s squared. And then there's a rule that says the Laplace transform of f of t, e to the, I don't remember what the letter I used, but let's say it's ct. This is equal to capital F of s minus c. So, put these 2 rules together, right? It's not just knowing them separately, it's merging things together, knowing them, their powers combined. What does this tell us for t e to the 3t? We'll have the minus 2 in front. Come to the Laplace transform of t. It should look like 1 over s squared, but because there's an exponential, we shift, right? And I think someone said t minus 3. I think they meant to say s minus 3, but of course, we all know that. S minus 3 squared. Yes? So that's, you combine these 2 rules to figure out the Laplace transform of t e to the 3t. Similar for e to the 3t cosine t, the Laplace transform we can just write down. Cosine bt is s over s squared plus b squared. And so this is going to be very similar here. We just have to remember we're doing a shift. So everywhere where we see an s, we put s minus 3. So 4 times s minus 3, s minus 3 squared plus 1 squared. All right, and then the last one. T cosine t, we look on the formula sheet and we say, formula sheet, you're nice. And it'll say s squared minus 1 over s squared plus 1 squared. So that's the last part, the t cosine t. There's a minus 4 in front. And the formula is s squared minus b squared over s squared plus b squared quantity squared. Now, what comes next for part A? Do we need to push it all together? No. And why not? Because we love ourselves. We would never force ourselves to do things we don't need to do. And unless the problem explicitly says, mush it all together, it may not use the word mush, but once you've done what it asked, you say, great, I've done what it asked, I stop. And so there's our answer. See, that's great. We could have put that one on the test. All right. Any questions on our part A? And let's go to part B. We'll need a little bit of space here. So part B involves an integral. Now, there's 2 places where integrals show up on the formula sheet. One place is convolution. And so what does convolution look like? We will talk more about this later on, but it involves integrals 0 to t. One function is a function of tau. The other one is a function of t minus tau, d tau. Is this convolution, and why not? What's the giveaway that this is not convolution? Well, notice the bound. We're not going 0 to t, we're going 0 to infinity. So if you see that 0 to infinity, it's like, well, that can't be convolution. So you might say, well, is there a place where there's an integral from 0 to infinity? And the answer is yes. Yes, there is. Okay, where is it? It's near the top. And this goes back to the definition of the Laplace transform. namely that the Laplace transform of f of t is this integral 0 to infinity of e to the minus st f of t dt. And this creates a new function which we call f of s. And we say, okay, well, there's a punchline here, right? We gotta unravel this. So when we're doing Laplace transform, sometimes we get so abstract we forget what it's doing. We're starting with the function f of t. We end with a different function f of s. But that function has meaning because it's a function. In other words, if you plug something in, the output means something. And for a particular value of s, what it means is, what's this value of this integral? So you can say, oh, if we see an integral from 0 to infinity, that means we're really using the definition of the Laplace transform. We want to carry out the Laplace transform and then evaluate it at the right spot. Now, what's the right spot? Let's rewrite this to be calculus friendly. You might say, what makes something not calculus friendly? Well, this is more algebra friendly. I don't like square root symbols when I'm doing calculus. So let's get rid of the square roots. So what's another way to write the numerator instead of as square root of t to the fifth? T to the 5 halves. Great. Cool. Now, the square root also covers this e to the 4t. The square root of e to the 4t downstairs becomes what upstairs? E to the negative 2t. Now, where did the negative come from? It came moving it up. Why was it a 2 at the end? Well, because the square root is like multiplying the exponent by half. So our great aha says, hey, this is like the definition of the Laplace, but at a very specific value. And so in particular, we have our idea. And ideas. We're going to find the Laplace transform of t to the 5 halves. Then we're going to plug s equals 2. And that's the answer. Okay, so the good news is we do have a formula for the Laplace transform of t to any exponent at all. What is it? Well, it's on our formula sheet. So the Laplace transform of t to the a is this gamma function, a plus 1, divided by s to the a plus 1. Okay, and again, you don't have to memorize this. Use your formula sheet. Now, you don't know much about gamma, but there are two things that you do know. And why do we know it? Because it's on the formula sheet. So the two things we know, gamma of a half is square root of pi, and gamma of any number plus 1, so beta plus 1 is beta, gamma, beta. Okay, all right. I'm going to move this up so we have space. And okay, so let's start with our computations. The Laplace transform of t to the 5 halves, according to this rule, is gamma of what?
5 halves plus 1.
5 halves plus 1. Good. And downstairs? S to the 7 halves. All right. Well, we're almost done, except we would like to clean this gamma up. So let's assume that we don't want any gammas. So we shouldn't want any gammas. All right, well, what's another way to say gamma of 5 halves plus 1? Well, we can apply the rule. That's 5 halves, gamma, 5 halves. Like, cool. But can we do better? Sure. You can say, well, you know, I can think of 5 halves as 3 halves plus 1. And now, apply the rule again. So we still have the 5 halves, and now it's joined by 3 halves. And then we have gamma of 3/2. But can we do better? Yeah, oh great, I love the enthusiasm. Okay, good. We can think of this as the 5/2 and 3/2 still in front, and 3/2 is 1/2 plus 1. So this is 5/2 times 3/2 times 1/2, gamma of 1/2. But can we do better?
No.
Well, I mean, we can, right? Gamma of 1/2.
I thought you meant do better in the sense of doing better the way we have it before, which you have yourself.
Okay. All right. So punchline here, we have 5 times 3 times 1 is 15. And don't forget, gamma of 1/2 is square root of pi. So there's 15 square root of pi. And then downstairs, 2 times 2 times 2 gives 8. All right. So we have 15 square root of pi over 8 times s to the 7/2. Now, is this our answer? And why aren't we circling it?
Because we still have to use the negative 2t part.
Well, right. We did step 1. Now, step 2. Plug in 2. So, our answer says that the integral 0 to infinity of t to the 5/2 e to the minus 2t dt, which is f of 2, and this is, here is our f of s, that's 15 pi over 8 times 2 to the 7/2. Now, if you are so inclined, you could say, 2 to the 7/2, that's really like 2 to the 3 plus 1/2. Oh, whoops, I forgot to write the square root of pi upstairs. And 2 cubed is 8, which you can put together with the other 8, so you get 15 pi, square root of pi, excuse me. And then 8 times 8 makes 64 square root of 2. And there you go. See? You can do fun integrals now. All right. So that's the idea for number 2. Any questions?
Why did we choose? Why did we choose s equals 2 here?
We chose s to be 2 because we looked at our integral. See how there was a 2 there? And he said, aha, that 2 matches that s. So it's like, if I plugged in s equals 2, then it's exactly what I'm trying to find.
Okay, thank you.
All right. On to number 2. Find the following. The inverse Laplace of 3 minus 7s squared over s minus 2, s squared minus 2s plus 5, and the inverse Laplace of 36 minus 7s squared e to the minus 3s over s cubed plus 9s. All right, so inverse Laplace of very explicitly given functions. Now, usually when we ask for inverse Laplace of very explicit functions, it more or less means one thing. It means partial fractions. I strongly suspect at some point on this test you will need to do partial fractions. So it's good to know how to do it. So let's do these problems and then we'll talk about anything that didn't get covered and we'll make sure we're comfortable. So let's start with part A. We have 3 minus 7s squared over s minus 2, s squared minus 2s plus 5. When it comes to partial fractions, one thing you have to do is say, have you factored your denominator as far as it'll go? Now the rule of thumb will be either it will be super easy for you to factor, or we will factor it for you. So the good news is they factored it for us. And on a side note for part A, when we look at this s squared minus 2s plus 5, we'd really like to rewrite it. Now we're not going to find roots. We're not using quadratic formula. What we're going to do is we're going to complete the square. So completing the square, we say, well, s squared minus 2s, what would I need to put on the end so that this was a perfect square? Plus 1, right? Divide the middle term by 2 and then square. So negative 2 divided by 2 is negative 1 and then square. And then you say, well, wait, I have 5, so you see it as plus 4. So this is s minus 1 squared plus 4. Now that will come up eventually at some point. We don't have to do it now, but we do need to do it at some point. That just confirms, by the way, we don't want to try to factor it because it's not going to factor in a nice way. Well, it does factor. It just gets a little complex. Okay, all right. That's a math humor is not going over too well in this exam review. Okay, no problem. So, when it comes to partial fractions, usually I would say there's two big mistakes that I see happen a lot with students. Mistake number one, I'll talk about now. It is they forget how to set it up properly. So what do? Well, you look at your denominator and you say, I'm trying to pull it apart. So in this case, we'd have an s minus 2 and an s squared minus 2s plus 5. And then upstairs, well, we have to plug things in. We have to put in the right form. So what goes over the s minus 2? Some unknown, a. What goes over s squared minus 2s plus 5? This is the part, something s plus something. So you have that extra piece added on. Now why the extra piece? Because this did not factor all the way down. We had to stop. So you have to account for that. That's why you have that extra piece. Now, a good rule of thumb is at the very least you can say the number of unknowns should match the degree of your denominator. And if it doesn't, a mistake has been made. Now, I'm not claiming if it does, then you're perfect. But if it doesn't, check yourself. Check yourself. Okay, so we say, great, now we have the form. And we'll multiply through, clear out the fractions because fractions have been a challenge for us throughout our math career. So we say let's try to avoid them. And okay, so the denominator completely cancels on the left. In the first term, the s minus 2's cancel, so we have a times s squared minus 2s plus 5. And then in the second term, the s squared minus 2s plus 5 cancels. So we get b times s plus c times s minus 2. Now, at this point, I would say there's generally two schools of thought for how to find a, b, and c. And that's what you need to do. You need to find a, b, and c. The two schools of thought, or at least the two most popular ones, are make good choices. Just like your family said, you know, when you're off to college, make sure you make good choices. Go to those exam reviews. That's a good choice. For example. The other one is you say, compare coefficients. So I would recommend make as many good choices as you can. When you run out of obvious good choices, start comparing coefficients. Is there a good choice for us to make here? 2. Why is 2 a great choice? Because it knocks off a good chunk. So essentially, if you have something where you have a 0, like here, plug in 2, you get a 0 downstairs, that'll become a good choice. So you say, plug in s equals 2. We get 3 minus 7 times 2 squared. Well, that's 3 minus 7 times 4 is equal to a. We have 2 squared minus 2 times 2 plus 5. And then plus 0. Right, that's the whole point. 0's a friend. We like 0. So great. 3 minus 28, also known as negative 25. 4 minus 4 cancels. That's nice. So we get negative 25 is equal to 5 times a. So what is a? It's negative 5. All right, now we know a. Are there other obvious good choices? 1? I don't know if 1 is a good choice necessarily. It's not a bad choice, but it doesn't cancel stuff. 0? Okay, we can try 0. I see the reason 0 has a better chance is we see there's this b times s. And when you plug in s equals 0, that would go away. Okay, we could do that. S equals 0. And, well, what would we have? The nice thing about s equals 0 is it's really easy to plug in. You get 3 minus 0 equals a times 5, but we know a. So that's negative 25. So I'm using the fact that we know a. Plus b times 0 plus c makes c, and then times negative 2. Okay, well that's great. We can move things around, and what does this tell us? Well, it tells us that 2c is negative 28. So what's c? Negative 14. All right, well, progress. All right, well, we have 2 down, and at this point, anything works, right? Because if you know 2 out of 3, plug in any value. Let me just talk through what you would do if you wanted to expand and compare coefficients, just in case you like to do that. So in our case, we would say, well, hey, we have 3 minus 7s squared. Over here, you'd have a times s squared minus 2 times a times s plus 5a, plus then you'd have b s squared minus 2 times b times s plus c times s minus 2c. And you group the coefficients by powers of s. So you have, okay, we have a s squared, and then we have a b times s squared, and those are our only s squared. So a plus b s squared. And what about our s's? Well, we have a minus 2a, a minus 2b, and a plus c. So minus 2a, minus 2b, plus c, s. What about our constants? We have 5a and minus 2c. And now there's the great game of matching. We say, okay, our coefficient of s squared has to match. So negative 7 has to match with a plus b. Our constant, 3, has to match with the constant, 5a minus 2c. And then what happens to this part? Yeah, see, there's no s on the left-hand side. That's really a 0s. So that has to be 0. And now you say, okay, well, we don't know b. Is there one of these which is easy to solve for b? Yeah, this one seems pretty strong candidate. We see that a plus b is negative 7, but we already figured out that a is negative 5. So this says negative 5 plus b is negative 7. So what does that say about b? Negative 2. Okay. Now, I said there were 2 places where people make mistakes when it comes to partial fractions. There's a third thing, but that's for part B. And but here's the second thing. A lot of people, oftentimes, they'll get the right form. They'll actually solve for the constants correctly. And then they forget to put them back in, which means that they get the wrong answer. They'll get a lot of points, but we're not after a lot of points. We want all the points. So make sure you take all that hard work and get rewarded for it. Plug back in what you found. So we currently have the following. This is still part A. We can now say that instead of doing this form, partial fractions is letting us pull it apart into easier to work with pieces. So we have that A is, where did we find A? Negative 5. So negative 5 over s minus 2. And I also will give a word of warning. Sometimes your 5s and your s's start to look very similar. And I am very confident that someone in this class, maybe not in this room, but over the whole class as a whole, will not be able to read their own handwriting and will interpret one of their 5s as an S's or one of their S's as a 5. So my piece of advice, clean handwriting. Slow down. Make sure you can read what you wrote. I know that sounds silly, but you know what? We want you to do well. Okay, B times S minus 2S. C minus 14. Now we're going to use the complete the square work we did. S minus 1 squared plus 4. All right. Are we good to go with the first part? Yes. Are we good to go with the second part? Not yet. All right. What's the issue? Well, on the second part, you see how we have this part as S minus 1? We don't want that. Well, we have it downstairs. We don't want this S. We want it to look like the downstairs. We want it to match. We want it to look like S minus 1. So we have to rewrite it. So we say, okay, we can do that. So what do? Well, the easiest thing is to say, I'll make the S into S minus 1, right? That's an easy thing to do. Say, look, if I want S minus 1, I'll make it S minus 1. But then you say, I have to make sure I adjust so it's actually the same. So instead of minus 14, now what will we have?
Minus 12. 16.
Some people, I've heard minus 12, I've heard minus 16. And I should say, I had to wake up at 1 a.m. this morning. So I don't know. No, it's minus 16. When in doubt, just expand. Minus 2 times minus 1 would make a plus 2. Plus 2 minus 16 is minus 14. It's okay to check your work. We're going to check it, so you should check it too. All right, we're almost ready to go and write down our final answer. We're going to use the fact that we can break up over addition, and we're really going to think of this second part as 2 pieces. We're going to break it up into 2 ways. All right? So the part where the numerator has S minus 1, the part where the numerator doesn't have the S minus 1. So we have negative 5, inverse Laplace, 1 over S minus 2, minus 2, inverse Laplace, S minus 1 over S minus 1 squared, and 4 I'll write as 2 squared just so we can spot it in our formula. Now looking ahead, I won't write the constant yet. This part is going to have S minus 1 squared plus 2 squared downstairs. And upstairs we're going to put a constant. What constant would we like upstairs? 2. Because the formula has a 2 there. And you might say, which formula? The sine formula. So if there's a 2 here, what do we pull out in front? An 8. Okay. And now our last step is to write the answer down. So we have negative 5. The Laplace inverse of 1 over S minus 2 will give us e to the 2t minus 2 inverse Laplace of S minus 1 over S minus 1 squared plus 2 squared. The fact that you see S minus 1 says that there's an exponential. Is it e to the t or e to the negative t? E to the positive t. And now that takes care of the S minus 1. So if once you have that e to the t, that says, now I think of this as like S over S squared plus 2 squared. And on our formula sheet, that shows up as cosine. Cosine 2t. Minus 8. Again, you see the S minus 1. You know there's an exponential. It's the same exponential as before. It's e to the t. After you got the exponential part, you say, now I think of it as 2 over S squared plus 2 squared. And use the formula sheet. That's sine 2t. And we found the inverse Laplace. Any questions on the process for this one? Cool. All right. Let's do part B. So, part B, the inverse Laplace of 36 minus 7s squared e to the minus 3s over s cubed plus 9s. Well, I'm writing it down so that we have it for reference. That's an S downstairs. That's not a 95. All right. So the first thing, before you tackle, you say, okay, I got to do some partial fraction action. So we write it down. 36 minus 7s squared e to the minus 3s, s cubed plus 9s. Are we ready to do partial fractions? And someone said no. So why aren't we ready to do partial fractions? Right. Okay. So here's the third mistake I often see is people try to do partial fractions when there's this e floating around. If you see an e, you can't not do partial fractions. Partial fractions is polynomial over polynomial. If it's not polynomial over polynomial, you can't do partial fractions. I mean, I see people write down a lot of stuff, but they're not doing partial fractions, and they're not getting the right answer. So you say, look, I can't do partial fractions in this form. So how do we do it? Well, this problem is so nice, we get to do partial fractions twice. So what we're going to do is we're going to use the fact that we can break up the numerator. So it's 36 over s cubed plus 9s, subtract 7s squared over s cubed plus 9s e to the minus 3s. Now I say we do it twice, but actually one of them will not be too bad. In fact, one of them is a freebie. Now notice here that we've moved the e to the minus 3s to the side. And that what we have is we have two pieces. Each one is polynomial over polynomial. Life is good. Which one do you want to do first?
The left hand.
36 over s cubed plus 9s. Okay. So first thing is, can we factor the denominator further than what it currently is? Yes. All right. So what does that give us? We get 36. How does that factor?
S times s squared plus 9.
S times s squared plus 9. Very good. We know our rules. It's something over s plus something s plus c over s squared plus 9. Similar as before. We have the s term is a constant, the s squared plus 9, there's a little extra upstairs. Okay, since we've talked through the process in the last part, part A, we'll do a little bit faster here. Clear your denominator. Once we've cleared our denominator, we get 36 is equal to a times s squared plus 9 plus bs plus c times s. Any good choices? 0. Okay. We plug in s equals 0. And what do we see? We get 36 equals a times 9, so that's 9a, plus 0. So what does that tell us about a? It's 4. All right. Any other good choices? If you were feeling very creative, you could try 3i. I don't necessarily recommend that. It works if you... The problem is people get lost when you have i's because there's powers of i's. So what can we do? Well, we say let's switch. So we'll do our gather coefficients. So we have a times s squared. Here you get a b times s squared, so that's a plus b s squared. Here you get a c times s. And then on the end you get a 9 times a. So that's gathering your coefficients. Well, again, comparing the two sides, for our constant terms, we see that 9a equals 36. Well, yeah, that's what happens when you plug in 0. So a equals 4. Our middle term, what does this say?
0.
It says it has to be 0. So we know what c is. C is 0. Well, how about the a plus b? What's true about that?
B is -4.
Well, a plus b equals 0. So since a equals 4, then we come to the conclusion that b equals -4. And now we have our ABC. All right, so with this in place, we get that, we'll make some notes here, 36 over s times s squared plus 9 is equal to, and we make sure we account for all our things, a is 4, so 4 over s, c is 0, b is -4, so minus 4s over s squared plus 9. Okay, that's the first part. Okay, now the second part. The 7s squared over s cubed plus 9s. I'm just working on polynomial part over polynomial part. Okay, what do we do here?
Take out an s.
All right, we can take out an s, top and bottom, and cancel. And we get 7s over s squared plus 9. And now what? And now we're done with the partial fractions. That's already partial fractioned out. So like, oh, ha-ha, ho-ho-ho-ho, ha-ha-ha. Okay, so that can't go any further. So the punchline here, all this tells us we have the Laplace inverse of the 36 over s cubed plus 9s, 4 over s, minus 4 over s squared plus 9, subtract, then we have, I'll go ahead and write this as 7, and don't forget your minus signs. Minus signs are easy to lose. S over s squared plus 9 e to the minus 3s. Okay, now the fun begins. 4 over s, what would that become? 4. All right, it's like 4 times 1 over s. 4. All right. And I can see I forgot to write down this s here after I had told people to be careful. There's an s, so I should have written down the s. All right. The 4 can come out. The s over s squared plus 9, what would that be? Cosine 3t. So 4 minus 4 cosine 3t. The 7, by the way, that's pretty easy. That's minus 7. And now we come to an interesting thing we haven't yet talked about, which is what to do if you see an e to the minus 3s. We've talked about like e to the 3t, but e to the minus 3s. Okay, so when you're doing inverse Laplace and you see an exponential function, what does that signal? That signals shift. And in particular, this signals you have an on-off switch. So u is our unit step function. There's an on-off switch happening. And where does that on-off switch kick in? That's where you look upstairs. So you say, we're kicking in at time 3, which means that we're going to have a t minus 3 inside our unit step function. Now you might say, well, what am I going to be turning on and off? Well, that's where you look and say, what's in front? Now, s over s squared plus 9, we already know what that is. That's cosine of 3t. But what is wrong? Is this what we write down, and why not? So remember, you have to shift. So we we see that e to the minus 3s. We know that there's that step function kicking in. We say, all right, just say, figure out what the inverse Laplace is of what it's attached to. And then, when you write it down, you add in the shift. So replace the t by t minus 3. That's not legible, so I'll write this again. So 4 minus 4 cosine 3t minus 7 u of t minus 3 cosine 3 times t minus 3. So exponential function signals shift. So it's the shifted version of cosine 3t, shifted over, so you start at time t equals 3. All right. Now what? Yes, box it. We're done. And we probably should use the color that shows up more. Aha! We're done. We can even put a double box, put some check marks next to it if we wanted to. All right. Good. Any questions? Now, before we leave this part, and because we have so many more fun things to do, and I can already see I've used up almost an hour on 2 problems, and there's 8 to go. The 2 hour is not looking promising. I'll try to go faster. Okay, but I just want to make sure we mention things that are useful. There's one thing we didn't see in these problems. I just want to make sure you're comfortable with. Suppose you saw something, we'll make something up. 3 minus 4s plus 5s squared. We're not going to carry out the whole problem. But what if it had, say, s minus 1 cubed, s squared plus 16 squared? So, in other words, can you handle powers? All right. What's the right decomposition? Well, let's start with the s minus 1s. How many terms will we have for the s minus 1? The answers will have 3 of them. There will be an s minus 1. There will be an s minus 1 squared. And there will be an s minus 1 cubed. All right? So if you see something to a power, you're going to work your way up. What goes upstairs over the s minus 1? A. What goes over the s minus 1 squared? Now this is the part that people are like, whoa. It is just b. There's not an extra s plus c. You might say, well, wait, why not? Well, because you clue on the s minus 1 part. You say, could just the s minus 1 factor further, not the s minus 1 squared, just the inside part. And the answer is, no, you got it all the way down. So you say, well, great, since it's all the way down, I don't need extra stuff. How about over to the s minus 1 cubed? C. All right, for the s squared plus 16, how many terms will we have? We'll have 2, because it's squared. You'll have s squared plus 16, which is really x squared plus 16 to the 1, and then you have s squared plus 16 squared. What goes on top of the s squared plus 16? Yeah, ds plus e. Because you're cluing off the inside, the s squared plus 16. That could be, well, that you couldn't factor it down all the way, so you have to have a little bit extra. How about over the s squared plus 16 squared? What do you put? fs plus g. And then all you need to do from here is solve for your 7 constants. But we'll skip that because we're already running a bit behind. But just make sure you know how to handle in case you do have repeated terms downstairs. I don't want anybody to miss any points. My secret goal is to have as few people take the final as possible. Okay. But to go with that, that means we want you to do well. Okay, so this one, great. Number 3, it's a matching problem. we're told that f of s is the Laplace transform of the square root of t squared plus 1. We're not given a formula for f of s. We don't have the tools to find it. We say, all right, and then we're asked to match each of the following to one of the options provided below. No justification is required. Now, on the exam, there is a matching problem. For the matching problem, there's no justification required. We don't check your work. We just check, did you get it right or not? And there will be 5 boxes for you to fill in. And so just be patient and work it through. All right, so let's figure stuff out. So this is testing what? This is really testing, do you know the rules? So what are we going to have handy? Formula sheet. We're going to be like, okay, I am not going to risk anything. I'm going to keep looking at my formula sheet and make sure I'm finding the rule I need. Okay, so the first one says, hey, I want to find the Laplace inverse of f of s quantity squared. Now, we should point out, we do know the Laplace inverse of just capital F of s. That is the square root of t squared plus 1. That's another way to write down what this is telling us. So, what do we do? Now, here's the thing. We are really good at knowing what you might try to put down. We're like really, really good at it. And because of that, we can guess your mistakes. So don't rush in. What would somebody want to be true? Well, somebody might say, I have this cool idea. I'll just move the square to the outside. And then square root of t squared plus 1 quantity squared, that's t squared plus 1. Life is good. I'm getting points. No, you are not, because that is not true. The Laplace and the inverse Laplace, they don't work well with squares. They work well with 2 things, addition and multiplying by a constant. Okay, so that's out. So we think to ourselves, okay, well, there's nowhere on our formula sheet that it has function squared. So we start to ponder. What's another way to write f of s squared? Does anybody know another way to write f of s squared? It's f of s times f of s. So it's a product of 2 things. And there is a formula on the formula sheet for handling the inverse Laplace of a product. What's the tool? It's convolution. So, according to this is going to be convolution. I'll use the notation which is the star. The convolution of the 2 functions, square root of t squared plus 1 with square root of t squared plus 1. Well, what does that mean? Well, the convolution is an integral. It's an integral from 0 to t. Okay, so that's looking pretty good for one of these 2. And then you say, okay, for the first one, I replace t by tau. All right, well, that's great. And then in the second one, I replace t by t minus tau. So this is it. This is the convolution. This is the square root of t squared plus 1 convolution with square root of t squared plus 1. So it's like, it's L. That's the first one. All right. Any questions on that one? It's one of the more subtle ones. Next one. The Laplace inverse e to the minus 2s f of s. Now, when we see e to the minus 2s, what does that tell us we're going to have? It's a shift and an on-off switch. So what should we be looking for in our answer? We should have a u of what? What's on the inside of u? T minus 2. So we look for anything with a u of t minus 2. And there's only one thing with a u of t minus 2. So that makes it really easy to say, oh, it has to be I. And it is. Because see, it's the shift function, well, sorry, it's the on-off function shifted over by 2, and then you replace the function inside by t minus 2. So, aha, we see the shift, so it must be that. Now this comes down to make sure you know how the exponential function works, because there's an exponential rule for taking the Laplace, and there's an exponential rule for taking inverse Laplace, and they are not the same. But we know that you'll look at both of them. So we will put both forms oftentimes. So just word of warning. I'm trying to be friendly to say that. Inverse Laplace of f of s over s. Is that something that we know? Is it on the formula sheet? It is on the formula sheet. What is it? It's the antiderivative, the integral from 0 to t of square root t squared plus 1. Okay. Great. Now, next one. We have f of s minus 1. Okay. So we start scanning our formula sheet. And we say, is there anything that looks like f of s minus 1? Does that show up? Well, if you scan towards the bottom of the formula sheet, you'll see something that says f of s minus f of 0. Where does that show up? What is that corresponding with? So this is the Laplace transform of f prime. So the Laplace transform of f prime of t is f of s minus f of 0. That's on the formula sheet. Now, look at the function. Our function here is square root of t squared plus 1. When you plug in 0, what do you get? You get 1. So we say, so what should we be looking for? According to this, what are we trying to do to our function, square root of t squared plus 1? Yeah, so we're looking for the derivative of the square root of t squared plus 1. Well, all right. We know how to take derivatives, I hope. T squared plus 1 to the half power. The half comes down. T squared plus 1 to the minus half power, because half subtract 1 is minus a half, times the derivative of the inside, which is 2t. The 2's cancel. So we're looking for t times t squared plus 1 to the minus a half. Does that show up anywhere? It shows up, yeah, it's e. All right. And one more. Okay. Now, notice here we took the derivative of little f. So little f is that square root of t squared plus 1. Now it says, hey, what about the inverse Laplace of big F, taking that derivative, f prime? Is there a rule for that? And what's the rule it corresponds with? So the rule, have you found it? Sorry, what? Yeah, it relates to t f of t is equal to something f prime of s. What goes in there? A negative sign. Yes. Don't forget that. So, in particular, if we were trying to take the inverse Laplace of f prime of s, then what this says is, hey, if you want to take the inverse Laplace of f prime of s, that's negative tf of t. So in our case, since we know what f of t is, we're looking for negative t square root t squared plus 1. Sorry, what? D? Okay. Now notice they put in both the positive and the negative version. So they may say, haha, we think people might forget the negative sign. So we're going to put in both. But there you go. That's it. We used the rules. And, I can't quite put my finger on it, but there's something about this problem that I really liked. But I will say as a piece of advice, don't try to wordle your way through to the answer. If you're like, okay, I see 3 letters, what could I fill in to make a 5-letter word? That is not how they wrote the problem. Because I'm not the one who wrote it. I like to have fun. So the first time we ever had a matching problem like this on an exam was on a final exam from a few semesters ago. The answer was bingo. And a lot of people did not find that. I felt bad. But, oh well, such is life. Okay. On to number 4. Find the Laplace of f of t, where f of t is piecewise. So make sure you know how to handle piecewise functions. Now there's a couple ways it might show up. It might say, here's a picture. You say, oh, okay, it does this in this range, does that in this range, does that in that range. Or more commonly, they say, hey, here are the behaviors. And it lists the pieces and saying, this is what it's doing over different ranges. Now, if we want to find the Laplace transform of it, we've got to rewrite it in a way that's Laplace transform friendly. How does one do that? Well, we have to write it essentially in a single equation. So here's how it goes. So we're not doing the Laplace transform yet. This is first learn to rewrite. So we start at the very beginning. It's a very good place to start. So where's the very beginning? It's starting from 0 and above. And remember, for everything about Laplace transforms, you only care what happens above 0. What happens below 0, we don't care. We ignore it. So we say, okay, what's the initial behavior? It's 4. All right, so here's our initial. Now, where do we change behaviors? 2. Right, we can see it. We see it goes up to 2. So wherever you change behavior, you're going to add an on-off switch. So this is saying there's a change at 2. And now, what's the change? Well, you say, what came after? You're turning that on, minus t squared plus 3t plus 2. So here we have on. And subtract what came before. So we're turning that off. So that handles the first transition at 2. Where's our next transition? 4. All right, so I won't write underneath everything, but u of t minus 4, something happens at time 4. What comes after? We're turning on. 18 subtract 5t. What came before? We're turning off. So in this case, the before is the minus t squared plus 3t plus 2. All right. So with this, we've written it in a single line. This goes a long ways to doing what we need to do, but it's not 100% yet. So the next thing that we have to do is we have to clean it up. Okay, so let's clean this up. Now what do I mean? Well, we're going to rewrite. So u of t minus 2, we'll just group things. We have minus t squared plus 3t plus 2 minus 4 makes minus 2. There's a u of t minus 4. And let's see, we have minus t squared, which makes a positive t squared. We have minus 5t, minus 3t makes minus 8t. 18 subtract 2 makes 16. All right, now one of these we're like, yeah. And one of those like, ugh. Which one is like, yeah, we like it? The farthest right one is, yeah. Now why is it so good? What's another way to say t squared minus 8t plus 16? It's t minus 4 squared. And the reason we like it is because, hey, we're like, wow, matching, matching. We love it when things match. Because whatever that u is attached to, the inside has to look like t minus that, right? If I see u t minus 4, what it's attached to needs to be looking like t minus 4. So that's why we like that. This one, not so much. All right, so what do? We don't give up. What do we do? Well, we work on rewriting it. Okay, so minus t squared plus 3t minus. There's a couple ways to do this. But here's one way that will work. You just have to be patient. Is I say, look, I don't want t. I want t minus 2. So I'm going to replace t by t minus 2 plus 2. True story, t minus 2 plus 2 is t. So I have t minus 2 plus 2 squared plus 3 times t minus 2 plus 2 minus 2. Now we expand. So the first part becomes, don't forget the minus, there's a t minus 2 quantity squared plus 4 times t minus 2 plus 4. And here we have a plus 3 times t minus 2, a plus 6, and then on the end we have a minus 2. So I've just expanded out and regroup. We have minus t minus 2 squared. Don't forget the minus distributes. Parentheses are friends. They give you lots of points. Minus 4 plus 3 makes a minus t minus 2. Minus 4 plus 6 minus 2 makes 0. Oh, that's very convenient. It's almost as if we planned it. But that's not true. We didn't plan that. But we'll still take it. Okay, so minus t minus 2 squared minus t minus 2. All right. And now we're ready. Okay, so here we go. The inverse Laplace of f of t. Well, that's the inverse Laplace. And again, because the inverse Laplace is so good over addition, we really think of it as 3 pieces. We say, well, there's the first piece. That's a 4. We'll talk about that. We have minuses here. We'll go ahead and pull the minus out. Minus the inverse Laplace. Sorry, not inverse Laplace, just Laplace. I got so caught up on the last problem. I had so much fun. I really liked it. And so, all right, gotta be careful. U of t minus 2 times t minus 2 squared plus t minus 2. And plus the Laplace u of t minus 4 squared. All right, we'll start at the beginning. The Laplace of 4. Do we know what that is? Yes, we do. What is it? 4 over s. Very good, very good. Okay, now, for the next one. Once we see a u of t minus 2, automatically, if we're taking the Laplace and we see u of t minus 2, we know that there's going to be an e to the minus 2s. That's automatic. Goes in. Now, what's attached to it? Well, here what you do is you say, okay, you see this t minus 2 squared plus t minus 2. This is, think of this as a second as f of t minus 2. What would f of t look like? Be t squared plus t. Right? Just imagine, replace all your t minus 2's by t's. T squared plus t. And take the Laplace transform of t squared plus t. That's what's going to be multiplied by the e to the minus 2s. So the Laplace transform of t squared is 2 factorial over s to the 2 plus 1. That's 2 over s cubed. Laplace transform of t, 1 factorial, which is 1, over s to the 1 plus 1, that's s squared. Okay. Plus I did not plan well. For the next part, what do we see? U of t minus 4. So what do we know is going to be there? E to the negative 4s. And then we say, okay, this t minus 4 squared, that's our f of t minus 4. What would f of t look like? T squared. What's the Laplace transform of t squared? 2 over s cubed. And that's our answer. I'll rewrite it so it doesn't look weird. 4 over s, subtract e to the minus 2s, 2 over s cubed, plus 1 over s squared, plus e to the minus 4s, 2 over s cubed. All right. Any questions on number 4? Okay, good. Good. We're picking up speed, by the way. That's a good sign. Number 5. Find the Laplace of the integral from 0 to t, tau cubed, e to the 4 tau minus 5t, cosine 2t minus 2 tau d tau. All right. Ah, wow. How exciting. Okay. Well, there's we kind of know right away what this problem involves. What is going to be involved in this problem? And why do we think that? Convolution. Why do we think convolution? You see an integral from 0 to t. That signals convolution. And in particular, you see things like t minus tau floating there. So we're like, okay, if we suspect convolution, then we start saying, what we want is we want integral 0 to t, a function of tau and a function of t minus tau. So once we see convolutions on the menu, we say, what's our f and what's our g? So let's start with the cosine and just talk about that for a second. Is there another way to write the inside of the cosine to make it either look like t minus tau or tau hanging out? I'm not being profound here. Just
2 times t minus tau.
Yeah, it's cosine of 2 times t minus tau. Like, oh, that says, hey, it's a t minus tau. Cool. And then you have the t cubed, and you're like, hey, sorry, not t cubed, tau cubed. Like, hey, that's tau cubed, that's cool. And then you have that. E to the 4 tau minus 5t. And how to handle that, that's what makes this problem fun. Now, there's a couple ways to do it. So I'm not going to try to pressure you. What can we do? Well, one way is if you're very creative, there are ways to break this up so you can say, I'll have a little bit go over here and a little bit go over there. But that can sometimes be a hard thing to spot. But let's just make a note of something. E to the 4 tau minus 5t, can we rewrite that using the properties of exponential functions? Yes. It becomes e to the 4 tau times e to the minus 5t. Correct? Because you can separate addition and subtraction upstairs by multiplying out. Now, why do I point this out? Well, you could rewrite this as tau cubed e to the 4 tau e to the minus 5t cosine 2 times t minus tau d tau with respect to the integral. What is e to the minus 5t? Constant. Because notice the integral is integrating with respect to tau, not t. This is when it's helpful to be able to differentiate your t's and your tau's. Since it's a constant, what can you do? You can pull it out. So you say, this says find the Laplace of e to the minus 5t, integral 0 to t, tau cubed, e to the 4 tau, cosine 2 times t minus tau, d tau. So what we can do is say, well, let's ignore the exponential in front. We have ways to handle exponentials in front. Now, does this look like convolution? It does. So in particular, let's go ahead and work out. So what we have here, what are our two functions? Well, the first function, this looks like your function t cubed e to the 4t. So we have the t cubed e to the 4t. Convoluted with our second function is cosine 2t. So that's just the integral part. All right? Do you see where the t cubed e to the 4t and the cosine 2t came from? So you want to make sure you can spot the functions. Essentially, anything with the t minus tau, that goes into your g, and just replace t minus tau by t. Anything with only tau, well, that becomes your f, and replace tau by t. Okay, so we're going to come back to this in a second. What's the rule for convolution?
It's L the first time, L the second.
Yeah, so the thing is, convolution is set up so that you can take the Laplace transform of the two things and you multiply the results. So we can take the Laplace transform of t cubed, e to the 4t, and times it by the Laplace transform of cosine 2t. Well, all right. So let's talk about t cubed. T cubed by itself, this would be 3 factorial over s to the 4th. All right, if all we saw was t cubed, 3 factorial over s to the 4th. What does the e to the 4t do? It's a shift. So instead of s to the 4th, what do we put? S minus 4 to the 4th. Okay, what about cosine 2t? What's that going to be? Well, that one's a little bit easier. It's s over s squared plus 2 squared. So s over s squared plus 4. So what we have is we get 6, that's 3 factorial, s over s minus 4 to the 4th times s squared plus 4. Okay, so that's the Laplace of just the integral. Now we have the e to the minus 5t. So we know for just this part, just this integral, it would be 6s over s minus 4 to the 4th s squared plus 4. What does the e to the minus 5t do? Okay, so in particular, what happens to s? Yeah, so now when we see our e to the minus 5t, this says, aha, s is going to become s minus minus 5 or s plus 5. So we end up with 6 times s plus 5 over s plus 5 minus 4 to the 4th s plus 5 squared plus 4. And we can clean it up just a little bit. Why not? 6 times s plus 5, because there's s plus 5 minus 4. I think we can do that. That's also known as s plus 1. And we'll leave the s plus 5 squared plus 4 as is. And there we go. Ha! See, that's not so bad. And in case you thought that was bad, I just want to add, whatever we put on the exam is always easier because Steve did not write the exam problems. Right? That's the good news. Any questions? All right, good. You're set for convolution. Okay. Number 6. We're starting to get towards the end of our Laplace stuff. Find the inverse Laplace of s arctangent of s minus a half log of s squared plus 1 plus natural log of s minus pi half times s plus 1. Okay. Well, it just wouldn't be a Steve Butler review without an arctangent. So you know we had to throw it in there. All right. Well, we have a problem. None of our formulas seem to directly be useful here. That's not a good sign, but that's okay. We start thinking and saying, all right, what can we do to make things simpler? And we see arctangent, and we say, you know, there's a reason the math professors love arctangent. When we look at arctangent, what's true about arctangent? I know you've learned so much about arctangent over the last couple of years. It's like there's so many things, Steve. There's the asymptotes. But in particular, I'm thinking derivative. What's true about the derivative of arctangent? 1 over s squared plus 1, which looks like polynomial. So you say, oh, taking derivatives gets us closer to things we're comfortable with. So an idea says, hey, if you have something which looks messy, but the derivative has the potential to look clean, and by that you say either you see a log or an arctangent, your mindset should be, let me try taking a derivative and let's see what happens. So I'm going to call this expression here, let's call this capital F of s. So take a derivative. Well, product rule. Derivative of the first is 1 times the second, that's arctangent of s, plus the first times the derivative of the second, 1 over 1 plus s squared. Okay, now the second one, minus a half. Here, to take this derivative, chain rule. Derivative of log says put the inside stuff downstairs, take the derivative of the inside stuff, put that upstairs. So minus a half times 2s over s squared plus 1. Derivative of natural log is 1 over s. Derivative of pi halves s is minus pi halves, and the derivative of plus 1 is 0. All right, this is looking better. Does anything simplify? Yes? Okay, it is s over s squared plus 1. That's true. Ah! Ha 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 ha! Woohoo! Woohoo! Yes! Nice! Okay, so we now have arctangent of s plus 1 over s minus pi over 2. That's already looking better. But could it be even better? Do we have a formula for arctangent on our sheet? No. No, our sheet is not all-knowing. So, but what can we do now? We can take another derivative. It's an idea so nice, we'll do it twice. Okay, what's the derivative of arctangent? Spoiler alert, we already did it. 1 over 1 plus s squared. Derivative of 1 over s? Negative 1 over s squared. Derivative of negative pi halves? 0. Now, can we take this inverse Laplace?
Yes.
Yes, we can. So you can say, the inverse Laplace of f double prime of s, That's the inverse Laplace of 1 over 1 plus s squared minus 1 over s squared. Well, inverse Laplace of 1 over 1 plus s squared is sine of t. Inverse Laplace of 1 over s squared is t. Now, is this our answer? And no, you didn't even let me ask. I was going to ask why not, but I think you've come to expect that from me. We've been together too long, too many semesters. I've become predictable. I'm sorry about that. Okay, this is not our answer, because we were after the inverse Laplace of f of s. We found the inverse Laplace of f double prime of s. Now is when we cross our fingers and say, is there anything that says these ideas are connected? So is there? The answer, it's on the formula sheet. There actually is one that connects. So I think it's written as Laplace t to the n f of t is equal to negative 1 to the n, the nth derivative of s. Or if you like, t to the n f of t is negative 1 to the n inverse Laplace of the nth derivative. Now, in our case, we can say, we did second derivative. So t squared f of t, negative 1 to the n is just 1. That's the inverse Laplace of f double prime of s. Now, what are we after in this formula? We are after just f of t by itself. So, what do we have? We have t squared f of t is sine of t minus t. So what do we do to get f of t? We divide by t squared. So our answer is sine of t minus t divided by t squared. And that's it. Okay, cool. Now, quick side note. Why is that there? That minus pi halves s plus 1. Because it didn't seem to do anything. Is there a reason it's there? Ha ha! To throw you off. Why, I would never. Okay, I might a little bit. In terms of solving the problem, it doesn't seem to do anything. But there is a reason why it's there. It actually does have to be there. So there's a little technical note. In case you're wondering, why is that there? Why did you bother putting it down? So one of the things that's true is that when you look at f of s, it has to be the case that as s gets big, what does f of s have to do? It has to go to 0. So if I'm a Laplace transform of something, I need to be going to 0. And if I'm not, something's wrong. So the problem is, if you only have this part, this does not go to 0 as you let s go to infinity. And so to actually make it a proper Laplace transform, so if you went to Wolfram alpha and said, hey, what is the Laplace transform of sine t minus t over t squared? It will have this extra part, and it is needed because that is involved. But in terms of the problem, you don't need to know that. I just wanted to point that out in case you go home and say, boy, why did Steve do that? Now, why did he put that extra stuff there? It's because the problem needed it, even if we didn't need it. All right. That gets us into our word problems. We're going to talk about 2 word problems. Now remember, there are 3 categories for word problems. Do you remember what the 3 categories for word problems are this semester? Okay, so we have tanks which are mixing, springs which are vibrating, and populations which are growing. Those are the 3 things: mixing, vibrating, growing. All right? So, we need to be able to handle those things. All right, so let's see what this one says. We have a 20-gallon tank full of brine. Brine just means salt water. So let's draw some pictures here. 20 gallons, okay. 4 gallons per minute of pure water enter the tank. Okay, so we have 4 gallons per minute. It's pure water, so that means there's no salt. And 4 gallons per minute are exiting the tank. Ah, good. It's nice to see when the entry and the exits match. So the levels will agree. And for Laplace transforms, they kind of have to. Otherwise, it gets really messy, unlike the messes that we already have. Initially, there's no salt in the tank. Okay, what is salt? Oh, x of t is the amount of salt. Okay, so we have that x of 0 is equal to 0. And then, starting at time 0, 3 ounces of salt are dumped in the tank once every minute on the minute. Now, should x of 0 be 3 or x of 0 should be 0? Let's just assume x of 0 is 0. Let's not ponder this. If x of t is the amount of salt in the tank at time t, then find the Laplace transform of x of t. The final answer must not involve an infinite sum. Well, that's suspicious. We probably will need an infinite sum at some point. So let's talk about what's happening here. So 3 ounces are dropped into the tank once every minute on the minute. So that says that salt isn't coming from the water. There's a chef or somebody, just once every minute, they just drop in some salt. There was a chef that was very popular who would be like, bam, and like, I'm adding the flavor, bam, throwing in the salt. Okay, so we just throw in 3 ounces every minute on the minute. What type of function captures that behavior? So there's like a spike, an instantaneous spike. What is that? It's delta. So this problem is a delta problem. So in your word problems, you should anticipate that you might see a delta or you might see a unit step function. So we have something interesting going on with our external things happening. So how do you recognize delta? It's something that happens at sort of an instantaneous moment. Your system changes. So this is sometimes called pulse or impulse. In particular, if you see springs, I'll talk about an impulse force, or just like once on the minute. It's just like it happens at an instantaneous moment. So we can say what? Well, we know our basic rule for x prime. We have in minus out. That's how it's always been. Now, our out is not so hard. We have 4 gallons per minute out of a 20-gallon tank. So how much leaves every minute? What proportion leaves every minute? 1/5, 4 over 20. So our out is 4 over 20x. Our in, well, we have 0 coming from the pure water, but then we have to account for the salt that keeps getting dumped every minute. So how do we capture that? Well, hard to do in this space, but okay. So we have the salt at time 0. So that's 3 delta t. That says, boom, I add something at time 0. Pow. How do I add 3 more ounces at time 1? It's another 3 ounces. Time 1 would be delta of what? T minus 1. How do I add 3 ounces at time 2? 3 delta T minus 2. When do I stop? Never. So this could be written as 3. I could do a sum from time 0 to infinity, delta T minus K. Okay, so rewriting this, we have x prime, the salt coming in, we have spikes at on the minute of 3 being added in, 3 delta T minus K, and then minus 1/5 x. Now, what do? We found our differential equation. We figured out, aha, we have this delta function coming in. We know how to write that. We account for every time that we add salt in. We have all our in salt. We know our out salt. What comes next in this problem? What are we looking for? We're looking, it's always good to remember what we want. We want to find the Laplace transform of x. So we have a differential equation. How do we use that to find the Laplace transform of x? Well, we look at the equation sheet, right? So we have a differential equation involving x. And we say, okay, what do? We throw the differential equation into the Laplace transform. So in particular, the Laplace transform of x prime is the Laplace transform of this sum k equals 0 to infinity 3 delta T minus K minus 1/5 x. So once we have our differential equation set up, we have to set it up. So that's the word part of the word problem. Translate that into the equation. And then say, okay, now let me do something to that differential equation. The answer is throw it into the Laplace machinery. You throw both sides in. Is there another way to write the Laplace transform of x prime? Yes. See, haha, you thought I was going to say no. Haha, I gotcha. I gotcha. I knew it was going to happen. All right. So, our formula sheet tells us that this side is going to be s capital X minus x of 0. What is x of 0? 0. All right. Now, the sum is a sum. Laplace transform works great with sums. So this becomes the sum, k equals 0 to infinity, this 3. Now, do we know the Laplace transform of delta T minus K? What is it? E to the minus ks. All right. And then minus 1/5 the Laplace transform of x, which is big X. Okay, and the moral is once we solve for big X, we're done. And there's not much left, right? Which is good because we don't have a lot of space. We can move the minus 1/5 x across. So we get s plus 1/5 big X is this sum. Let's go ahead and bring the 3 out. Now, unfortunately for us, we have to pause here and say, troubles. We have a small technical thing. in that we have an infinite sum. And our answer should not have infinite sums. So how do we get rid of it?
Well, there's a special thing for
Well, there's two sums that we know how to handle. It's almost like it would be on the formula sheet. So one sum looks like k equals 0 to infinity of z to the k is 1 over 1 minus z. And the other one, sum k equals 0 to infinity of z to the k over k factorial is e to the z. Does one of these look like we can make it work? Though this one we'd have to have a k factorial. There's no k factorial, so that looks very unpromising. So maybe we should think of this first one. Something to the k. Well, e to the minus ks, you can think of that as e to the minus s times k. All right. Well, then if we apply this rule, we get a 3, 1 over 1 minus e to the minus s. And notice there's no infinite sum. So we're using properties of our sums. And these are on the formula sheet, so they're fair game. Is this our answer? No, it's not, but it's close. We just have to divide. So our final answer is x. We get 3 over 1 minus e to the minus s times s plus 1/5. And that is our answer. All right. And we don't have to solve for little x, because that's not what the problem asked us to do. We only do what the problem asks us, because, well, that's how we get the points. All right, any questions on this one? Okay. Number 8. A spring mass system without a damper is set up with a mass m equals 4 and a spring constant k equals 36. Initially at time t equals 0, the spring is at rest in its neutral position. So that means x of 0 and x prime of 0 are 0. If an external force of 24 cosine 3t acts on the mass between time 0 and pi and no external force for time above pi, then determine the motion of the spring. How is the spring moving? Okay, do we know what type of problem this is? Yeah. It's kind of hard to miss. Once you see spring mass, spring mass damper, whatever you see spring, you're like, great, I know where we are. If you see a spring problem, you know that there's a formula for springs. And it goes the following. mx double prime, mass times acceleration, cx prime, I'll talk about what c is, kx, this is Hooke's law, equals external. Now m is mass, c is your damping constant, and if there's no damper, it's just automatically 0 because no damping is happening. K is your spring constant. You say, all right, if I see a spring problem, I know I have this formula. Okay, do you want me to decrypt the statement I said earlier about you can kind of expect what problem will be on this exam? If you think back to our first review, I said there were 3 types of word problems. You will see all 3 of them this semester. Just think about what kinds you haven't seen yet. Okay. I digress. Now we're like, wait, I don't remember. What was on the first exam? It was so long ago. All right. So, if you are anticipating a spring problem, you're going to be like, I have this formula emblazoned on my heart. I just know it. because it's not on the formula sheet. You have to know this one. You say, all right. So you start figuring out what goes where. Well, we have M, we have K, and there's no damper, because it says no damper. So we say cool, 4x double prime plus 36x. Then the external force. Now we think about external force. When we're in this Laplace transform once, we tend to look for external forces for springs where we either hit it with a hammer or we have something that acts for a while and turns off. Hitting with the hammer is the delta. You look for pulse or impulse. Turning on or off, you look for something that's sustained over time. So are we turning on or off, or are we hitting it with a hammer? We have an on-off. Because this force acts for a length of time. Okay. Cool. So, with this in mind, we say we know our external force is piecewise, because we see that something happens. So, in particular, our external force, we could write it as it's 24 cosine 3t for 0 less than or equal to t less than or equal to pi. And then there's no external force, also known as 0, if t is greater than pi. But of course, that's not going to help us find the answer, because that's not Laplace transform friendly. So we rewrite it using our tools. What will this become? Well, you start with the initial behavior. What's the initial behavior? It's 24 cosine 3t. Where do we change behavior? At pi. So we have u of t minus pi. What's our behavior after pi? 0. What's our behavior before pi? 24 cosine 3t. Yes? Right? We have our on-off. We have our after, where we turn on. We have our before, which we turn off. Okay. Are we ready now to take the Laplace transform? No, we're not, but we're so much closer. What's our issue? It's over on this part. What's wrong with this t? Yeah, it's not t minus pi. It's just t. Okay, so we got to fix that. 24 cosine 3t. Subtract u of t minus pi, and there's a 24 cosine, and we'll do our classic. This is 3 t minus pi plus pi. Okay, so maybe we should do some notes on the side. So if I have cosine 3t minus pi plus 3 pi, what does that do? What does that plus 3 pi do?
Switches the sign.
Right, it switches the sign. So why does it switch the sign? Think about the picture. You have the unit circle. You're at a point. Let's say here's our point. If we go 3 pi, you go once around is 2 pi, then another pi gets you exactly opposite. So that your x and y coordinates both change sign. So the punchline is that this is equal to negative cosine 3 times t minus pi. And so we need to update that so it looks in the right form. So this is something that we do need to do here. Okay, so we have, in particular, 4x double prime plus 36x is equal to 24 cosine 3t minus makes a plus u of t minus pi 24 cosine 3t minus pi. Okay, now are we ready to do Laplace transform? Yes. We do it to both sides. We are equal opportunity Laplace transform takers. So, on the left-hand side, we get 4. The Laplace transform of x double prime. What will that be? Well, on our formula sheet, it's s squared capital X, subtract, and now I double check, s little x of 0, subtract little x prime of 0, plus 36 capital X. On the right-hand side, 24 is a constant. Laplace of cosine 3t. Anyone know that one off the top of their head? S over s squared plus 9. Cool. And then u of t minus pi. That says we're going to have an e to the minus pi s. We still have a 24. And still s over s squared plus 9. Okay. Do we know x of 0 and x prime of 0? Yeah, because they told it to us. So you have to have initial conditions to apply Laplace transforms. So if you're applying Laplace transforms to solve a differential equation, you have to have initial conditions. So it'll be somewhere there. They either will be explicit or they'll say something like, oh, I'm at rest, or I'm just relaxing. You know, I'm just taking it easy on a Sunday. Okay. Cool. Cool. So, we are almost there. Well, this makes the left-hand side pretty straightforward. You can pull an x out. You can also pull a 4 out. So you have 4 times s squared plus 9 times x equals, on the other side, 24 s over s squared plus 9 plus u negative pi s 24 s over s squared plus, s squared plus 9, which tells us, because we're running out of space, it's trying to get us to our answer quickly, divide. Get x by itself. So the process of using Laplace transforms is you set up your differential equation, take the Laplace transform of both sides, solve for x. We're in the solve for x stage. So we get that capital X, what we're after. Well, when you divide by 4, you get 6 s over s squared plus 9 squared plus e to the minus pi s. Again, divide 24 by 4, you get 6 s over s squared plus 9 squared. Okay, are we done at this stage? We are not. What is it we were after? What did the problem ask us to find? Know where your stopping point is. What are we looking for? This is x of t. What did we find? Or what have we found right now? We have found big X of s, not little x of t. So how do we get to our answer? The inverse Laplace. Okay, so I might be able to squeeze it here. So our answer, x of t, is the inverse Laplace of capital X of s. Okay, so, well, 6 is 6. S over s squared plus 9 squared. Does that show up anywhere? Actually, maybe I shouldn't put this 6 yet. We have s over s squared plus b squared squared. Is that on our formula sheet? Well, if you look at Laplace of t sine bt, it is 2bs over s squared plus b squared squared. Let's see what we have here. We certainly have the s squared plus something squared squared. On the top we have s. What would we like attached to this s? 6. 2b. Ah, I have a 6. So that says this part right here is exactly the inverse Laplace of this would be t sine 3t. Okay, now we come to this part. We say, the e to the minus pi s says there's an on-off switch happening. So u of t minus pi. And then we say, hey, I've seen this before. It's that. So it's the same function, almost the same function, except it's not the same. What changes? Shifts, right? So it's going to be t minus pi times sine 3 times t minus pi. And now what do we do? Yeah, box it. Because that is our motion as a function of time. Good, good. Life is good. All right. See, these aren't so bad. They only take a page. Okay, so we've done 8 problems, and I know I have just gone over time. But I will say the last 2 problems are useful to know, because the last 2 problems are about series. And there will be 2 questions about series. We're going to talk about 2 main ideas. So the 2 main ideas you need to go and be able to be comfortable with are recurrence relationships and finding the first couple of terms. So let's look at number 9. We're given y is the sum from 0 to infinity of cn x to the n. And we're told it's a solution to this differential equation, y double prime plus 4 minus x squared y prime plus 3y equals 0. Find a recurrence relationship for the ci. So in other words, for the coefficients. And this says include when the recurrence holds. And then there says, hey, we're going to give you the initial conditions, find the first couple of terms. Okay, so we're going to hold off on the second part. And we're going to start with the first part. So what are we doing? All of this, for this problem, the next problem, when we talk about series, it all comes down to polynomials. Think of series as these huge, gigantic polynomials because they are huge, gigantic polynomials. And so you get into the mindset, what do I do with polynomials? I gather coefficients together. I group coefficients, like we were doing for partial fractions. So when we talk about recurrence relationships, it's the same idea. It's like we just are going to be grouping coefficients together. So what's the process? Well, I would say the first process, I'll call this step 0, is we're going to expand. So when I say expand here, if you see something like this 4 minus x squared, I'm going to multiply that into 2 pieces. Y double prime plus 4y prime minus x squared y prime plus 3y equals 0. Okay. Now, after you expand, what comes next? Well, I should have probably come in with a list, because I'm just making this up as I go here. But this is good. This works. Now, one is you're going to, next step, you replace your y prime, your y double prime, and anything else. But at this stage, we're just doing some basics. You should not expect to see anything above y double prime. What do we mean by replace? Well, we know what y is, because we're told what y is. So we're going to replace these by their sums. Okay, so let's talk about our pieces here. We know y. It's the sum 0 to infinity Cn x to the n. What is y prime? Does anybody know this one? Just take the derivative of each part. N Cn x to the n minus 1. And y double prime, which I won't have enough space, but that doesn't stop me from writing it for some reason. Foolishness. N minus 1 Cn x to the n minus 2. Just keep taking derivatives. You can, but there are some times when you say, let me hold off and see if I want to. Because if you have powers of x in front, you might be like, I don't think I want to do that. Okay, so now what does that say we have? So for y double prime, we'll have the sum n equals 0 to infinity of n minus 1 Cn x to the n minus 2 plus 4, we put in the y prime. Sum n equals 0 to infinity n Cn x to the n minus 1 minus x squared, sum n equals 0 to infinity n Cn x to the n minus 1 plus 3, sum n equals 0 to infinity of Cn x to the n. Okay. Any questions up to this stage? Now, before I go to the next step, I want to put any powers of x into the sum. And this is why it's important to expand first. Because we really want to put in only powers of x. We don't want to put in like 5 plus x. We only want to put in like x. And there's only one place I have to do that on this problem, which is right here. So this means I have to rewrite it, and it's almost all going to be the same. Oftentimes, if I were doing this on a test, I wouldn't do this all written out. But because I'm in front of a live studio audience, I will. All right, so we're just copying. We're making sure we don't make any mistakes. So here's the part where we have to pay attention. The x squared comes in. We have x squared times x to the power n minus 1. What does the new power become? It's x to the power n plus 1. Okay. Now, the next step. And here's the fun part. For the next step, we want to shift. And when I say shift, what I mean is I want to have all of my powers look the same. The goal, remember, our goal for all of this is I'm trying to group coefficients. So to help me group coefficients, I want my powers to look the same, because then I know how to put coefficients together. So when we talk about shifting, we say, okay, I want to make this look like, is k okay for a letter? Sure. All right, good. So I'm going to say on this sum, I want n minus 2 to equal k. Now that's just for this sum. And when we do that, we're going to say, well, now this sum is going to have x to the k power. But we have to figure out how all these other n's change. Well, n equals 0. When n equals 0, what is k? Negative 2. Now, if you're feeling uncomfortable, don't worry. It'll work out in a second. If n minus 2 equals k, what is n? K plus 2. Right, you can just add 2 to both sides. What is n minus 1? k plus 1. Do you see where this is coming from, or does it just feel like, oh, Steve's just bluffing? If n minus 2 equals k, another way to say this is n equals k plus 2. And then the Cn, which I didn't leave enough space for, Cn becomes C sub k plus 2. All right, in the second sum, this is a different sum, so I get to make a different shift. I want x to the k. So I say, now n minus 1 is k. So we'll have plus 4, sum, and, okay, n is k plus 1. C sub n is c sub k plus 1. X to the n minus 1 is x to the k. Where do we start the sum at? When n equals 0, k is -1 to infinity. Okay, for the next sum, what's our shift? What does k equal? It's n plus 1. Okay, so we have our sum. N is k minus 1. So k minus 1, c sub k minus 1, x to the k. Where do we start the sum at? Started at 1. For the last sum, oh, this last sum, what's going to happen here? What's the shift? The shift is let n equal k. It's like, okay, sure, why not? Now, essentially what you're doing here is very much like substitution. And it is. It's essentially just saying, I'm just changing my indexing variable. I'm just calling it a new name. But I'm doing it in such a way to prepare to group things together. Okay, so we've done our shift. This is probably the most important step. So don't feel rushed. Take your time. After you do your shift, now you do your peel. Now when I talk about peel, I say I'm going to pull off terms at the start. And I want to pull it off so I can have a common starting point. So we look at our current starting points. We have -2, -1, 1, and 0. And we say, well, among those, which value is the highest? Where do we start? So our starts for -2, -1, 1, and 0. What's our largest start? At 1. So the moral is, I want all my sums to start at 1. So what do I do with the sums that don't start at 1? I pull off the first couple of terms. So let's start with this sum. Plug in -2. What comes out? 0, because of the k plus 2. Plug in -1. What comes out? 0, because of the k plus 1. Okay, so this starts as 0 plus 0 plus. Plug in 0. What comes out? 2 times 1 times c2, x to the 0. So that's 2c2. And then you're up to 1. 1 to infinity, k plus 2, k plus 1, ck plus 2, x to the k. Okay, so this is our peel. Pulling off the first few terms until we get to the common start. And the common start is whichever one has the last start. When we come to the next part, when we plug in -1, we get 0. When we plug in 0, we get C1. And we actually get C1 x to the 0, I should point out. But since x to 0 is 1, we just call it C1. And then we're at our start. So 1 to infinity, ck plus 1, x to the k. Now here, do we have to peel? No, this one is not appealing. It's a math humor, right? You've got to lighten the mood. Okay, so we don't have to peel because it's already starting in the right place. So 1 to infinity, k minus 1, ck minus 1, x to the k. Finally, the last one. We peel the term n equals 0. What does that give? C0. And then everything else. 1 to infinity, ck, sorry. Why did I put an n here? It should be a k. K equals 1 to infinity, ck, x to the k. All right. Do you understand shift and peel? Good. Then the next step is combine. So you shift first, you peel, get a common start, combine. So let's combine the stuff that doesn't go into the sum. We have the 2c2, the 4c1, and the 3c0. So 2c2 plus 4c1 plus 3c0. That's not part of our sum because it doesn't follow the same rules. Anything that you had to peel off has to be treated separately. Plus one sum. One sum to rule them all. And here we go. It starts as k plus 2 times k plus 1, c k plus 2. So we're grouping our coefficients. Here, don't forget the 4. So then we have plus 4 ck plus 1. Here, don't forget the minus. Did I forget something here? There should be a k minus 1. Wait, what? Oh, wait. Yeah, k plus 1. Ha! I am so sorry. This is why you check your work. K plus 1. C, k plus 1 times k plus 1. There we go. All right. Minus k minus 1, c sub k minus 1. Plus 3ck, x to the k. Now, once you've done all of this, you've run out of space on your page. But the good news is, you've also have basically got the answer. Where's your recurrence relationship? We've written it down. This is your recurrence. That's what the problem was after. So, what we have is our recurrence says k plus 2 times k plus 1 ck plus 2 plus 4 times k plus 1 c sub k plus 1 minus k minus 1 c sub k minus 1 plus 3 c sub k is equal to 0. Now you might say, wait, where did the equal to 0 come from? Well, you see, we stopped writing equal 0, but this is equal to 0, and all this is equal to 0. And what you have is polynomial equals polynomial. When polynomials match, coefficients match. Since all the coefficients are 0, all of these coefficients are 0, which says that this expression has to equal 0. All right. So, we got the recurrence. Good. Are we done? No. We're also given y of 0 equals 4, y prime of 0 equals minus 2, and we want to find C0, C1, C2, C3. Now, some good news is you've got at least one free point coming right now. If you have some initial conditions, you have the starts. So for example, y of 0 is also known as C0. And y prime of 0 is also known as C1. Now, why is this? If you just think about what your sum looks like, you have your sum n equals 0 to infinity of Cn x to the n. When you plug in 0, what happens to your terms? Well, most of them become 0 because you have 0 attached to it. Which one doesn't become 0? The one that doesn't become 0 is x to the 0, which is the C0 x to the 0. If that doesn't convince you, you could say, hey, this is the same as C0 plus C1x plus C2x squared plus dot, dot, dot. The sum is just another way of writing that out. Now say plug in x equals 0. Ah, yes, that does in fact become C0. Okay. And what about y prime? Well, y prime is C1 plus 2C2x plus dot, dot, dot. Again, plug in 0, and you see that everything drops out except the everything drops out except the C1. Nope. Nope. I just explain things because it's hard for me to get out of teaching mode. I apologize. You're probably like, Steve, you didn't need to give a 3-hour lecture. But I like people to know why things work. Because I think if you know why things work, you have a better chance of remembering to use it correctly. Okay, so we've got 2 freebies. We're halfway. Woohoo! Now, here's the fun part. Once you get past your initial conditions, then you say, okay, the next C, this will come from your constant term, your constant coefficient. And then the next term after that, this is going to come from your x to the 1 coefficient. Okay, so you might say, what do you mean by your constant coefficient? Well, remember how we group things together? This part right here is our constant coefficient. This also equals 0. So if I want to find C2, I say, well, hey, I know that 2C2 plus 4C1 plus 3C0 equals 0. And I know stuff. Knowing stuff is really good. It's highly recommended. 4 out of 5 dentists recommend knowing things. So 2C2, what is 4C1? Well, C1 is negative 2, so 4C1 is negative 8. 3C0, well, C0 is 4, so that's plus 12 equals 0. Okay, 12 minus 8 is 4. You move it across. 2C2 is negative 4. That says C2 is negative 2. So now we have we have C2. We know what C2 is. All right, so maybe we should make a box here with our answers. So we said C0 is initial condition. We got that for free. C1, initial condition. Got that for free. C2, we used the constant coefficient, figured out that's negative 2. And then C3, well, where do we get that from? That's the recurrence. Oh, we forgot to mention one thing about the recurrence. When does the recurrence hold? So when is this true? For which values of k is this recurrence true? Look at your sum. The recurrence is, this expression is coming from your sum. Where does your sum start? 1. This is for k greater than or equal to 1. They may not ask you this, but if it does say, when does your recurrence hold? You say, once I figured out, I've pushed everything together, wherever my sum starts, that's where it holds from there on. So if your sum starts at 0, it's true for all k. If your sum starts at 2, it's true for all k greater than or equal to 2. So just keep that in mind. All right, now, how do we get our last coefficient? Well, we say, hey, now we're just going to go into the recurrence relationship with k equals 1, because that's our next power of x. Okay, so here we go. Recurrence with k equals 1. So 3 times 2 times C3 plus 4 times 2 times C2 minus 1 minus 1, which is 0, times C0 plus 3 times C1 equals 0. So I'm plugging that into the recurrence. My first time the recurrence holds. And we say, well, hey, we've already done work. So we have 6C3. We know C2 is negative 2. So 4 times 2 times negative 2 is minus 16. 0 times 4 is 0. Then 3 times C1, well, that's 3 times minus 2. So that's minus 6 equals 0. Or C6C3 equals 22. So C3 is 22 over 6, also known as 11 over 3. It's possible you might see a fraction, but not many. All right, that's number 9. So the recurrence relationships, once you understand this idea of expand out, replace all the y's, shift, peel, combine, it's going to go quick. If you understand the idea, it's all mechanical. And the biggest obstacle you'll have is forgetting to copy stuff down like I did. Practice. Okay, let's finish up. Number 10. We've made it this far. Let's go all the way. So, y is the sum, 0 to infinity, cn x to the n. Determine c0, c1, c2, c3, given y prime plus 2y squared equals 6x e to the 2x, and y of 0 equals 1. Now, notice what this problem does not ask us for. What does this problem not ask us for? Recurrence relation. If a problem doesn't ask you for a recurrence relationship, don't find it. That'll be harder. Be nice to yourself and say, well, look, what do I need? You say, okay, I have y of 0. Y of 0 gives me what? C0. So we say, we have C0. This is from our initial. Then how do we find C1, C2, and C3? Well, what we're going to do is we're going to make both sides into polynomials. So everything's going to be a polynomial, and we just start working our way up. So this is going to be the coefficient of x to the 0, if you like, the constant coefficient, the coefficient of x to the 1, and this is the coefficient of x squared. Do I care about the coefficient of x cubed? Or x to the 4th? Or x to the 5th? No! No! None of that will help me. I only need to figure out what's happening up to x squared if I think of both sides as polynomials. So I say, no problem. I'm great with this. So let's start with our y. And we have y is c0 plus c1x plus c2x squared, dot, dot, dot. We have y prime. What does that look like? Up to the x squared part. It starts as c1 plus two c2x plus, you almost have to imagine what the next term will look like, 3c3x squared, and dot, dot, dot. Dot, dot, dot says, ha, I don't care. It doesn't matter to me. Okay. How about e to the 2x? Let's talk about that for a second. Or maybe let's talk about x e to the 2x. So that's x. Do we know what e to the 2x looks like? Well, we turn to our handy-dandy formula sheet which says e to the z is the sum, 0 to infinity, z to the k over k factorial. And again, you don't have to memorize that part. That's on the formula sheet. So what does e to the 2x look like? So this says e to the z, by the way, looks like 1 plus z squared over 2 factorial plus dot, dot, dot. So e to the 2x, how does it start? 1. And then the next term? 2x. And then, haha, trick, it's dot, dot, dot. And you're like, oh, Steve, no, you stopped too soon. You were supposed to go to the next term. Or was I? See how there's an x there? This is really x plus 2x squared plus dot, dot, dot. Now, if you go extra terms, no problem. It's just ink. Ink is cheap. Or maybe it's pencil lead. I don't know. Maybe a lot of people write with pencil these days. It's very retro. All right. So let's talk about, we talked about this x e to 2x. We talked about y. We talked about y prime. Let's talk about y squared. Let's do that. So y squared, well, that's y times y. So that's c0 plus c1x, c2x squared, dot, dot, dot. c0, c1x, c2x squared, dot, dot, dot. Okay, how do you get constant terms? If you multiply this together, what would your constant term be? The only way to get a constant is constant times constant. c0 squared. And that's your constant term. What would your coefficient of x look like? c0, c1, and c1 times c0. Well, you could actually put those together and say that's 2c0, c1. And by the way, in case anyone's like, oh, this kind of feels like convolution. It is. It's a different kind of convolution, but it's the same philosophy. What's your x squared term look like? c0, c2, c1, c1, c2, c0. So we're just, think of going up and down. So 1 times x squared, x times x squared times 1. That's how you get your x squared. So c0, c2, c1 squared, c2, c0. So that would be 2 c0 c2 plus c1 squared. And then we don't care about the higher terms because we know that the information we've been asked to find, we only need to figure out what happens up through the x squared coefficients. Okay, so here's the punchline. We now put this all together. So y prime, we put in what y prime is. It's c1 plus 2c2x plus 3c3x squared plus 2y squared. Okay, c0 squared plus 2c0c1x plus 2c0c2 plus c1 squared x squared dot, dot, dot. Always include the dot, dot, dots. It's good habit. Equals 6 x e to the 2x, which is 6 times x plus 2x squared plus dot, dot, dot. Okay. Our constant terms. X to the 0. From the first we have c1. Then 2c0 squared. And it's going to be equal to the constant term on the right, which is 0. Now, by the way, we didn't say what c0 is. What is c of 0? c0 is 1. Okay, Well, so that says C1 plus 2 equals 0. So C1 is negative 2. All right. Now let's look at our coefficient of x to the 1. From the first term, what do we have? The y prime part, what do we have? It's 2c2. From the second equation, well, don't forget this 2. Numbers distribute. So it's 4, because it's 2 times 2, c0, c1. So plus 4c0, c1 equals, and the coefficient of x is 6. But the point is, we found the lower terms, the c0, c1. So we know that c0 is 1, c1 is negative 2. So this tells us 2c2 plus 4 times 1 times negative 2 is equal to 6. All right, well that's minus 8. Add 8 to both sides. 2c2 is 14. So c2 is 7. Okay. X squared. We're going after the coefficient for x squared. From the first term, 3c3. From the next term, remember to multiply the 2 through. Plus 2 times 2c0, c2 plus c1 squared equals, coefficient for x squared on the other side, 12. Okay, so 3c3 plus 2 times c0, which is 1, c2, which is 7, plus c1 squared, negative 2 squared. All right, all that equals 12. Well, okay. 2 times 1 times 7, that's 14, plus 4 makes 18, times 2 means all of this is 36. Move it across. 3c3 is 12 subtract 36, which is negative 24. Divide c3 is negative 8. So, we'll put our box here that says c0 comes from initial conditions, c1, our coefficient for x, c2 worked out, our coefficient for our constant, c2 is our coefficient for x, and c3 our coefficient for x squared. And so I don't want you to think that, oh, this looks complicated. It's really just, hey, everything looks like polynomial. That was our lesson from the end of Calc 2. Since everything looks polynomial, write down the polynomials and compare coefficients. So everything for series is about polynomials.